Basis and dimension. In this section, we want to combine the idea of linearly independence and spanning to see what that produces. What that gives us is the definition for a basis for a vector space or a basis for a subspace. That basis, that concept, is most important in the study of linear algebra. The definition says that let V be any vector space and let S, which has within it n vectors, is a finite set of vectors in V. Um, Basically, S is the subspace. Then S is said to form a basis for V if the following two conditions are both true. One, that S spans the vector space, and also that S is linearly independent. So we check both, um, and I have a theorem that kind of helps us navigate some of that so you don't have to do all the work. And because of the monster theorem, if the set is um, uh, so that you have n vectors and you're talking about an n space, if you're talking about R3, and if I'm given three vectors, then just check the determinant, because the monster theorem says that determinant is equivalent to everything else. If you're in the two space and you're given two vectors, then check the determinant. We can only do the determinant for square matrices. Now, if it's awkward, where if you're in the three space, they give you four vectors, then you can't check the determinant. Or if you're in the three space and they give you two vectors, you can't check the determinant. But you can use this neat theorem that I'm going to give you, and that's what I use. So let's look at some examples of bases. The standard basis for Rn, we call it the Euclidean basis. E sub 1 is equal to the 1 there in the first position, then zeros following, and then you can see E sub 2 and so on. In calculus 3, in the third space, we call E sub 1 I, E sub 2 is J, and E sub 3 is K. And and they look like, the I is the 1 0 comma 0. This is for the third space, right? So these are just unit vectors. But they form the basis. So the number two, the standard basis for polynomial functions of nth degree, um, is listed here. Notice that the count would always be plus 1 for number 2. Now the count here, or the size, would be n. If it's the three space, then I'm talking about three vectors basically. Here for this one, the size would be n plus 1 because of that constant. Later on, we call this size number the dimension. Here, for the number 3, the standard basis for the 2 by 2 space of 2 by 2 matrices. Notice how the count would be 2 by 2 is 2 times 2, so you get 4. So here the size is 4, and then down here the size is n times n. So let's look at this very neat theorem. And a note here on 3 and 4, you can see how the identity matrix basically forms the basis. and so you get exactly what you want. This theorem is most important. Let S be that same subspace before, but it doesn't have n vectors in them. I say here we have R vectors. Be a set of vectors in Rn. So within Rn, the size here is n. But this size, there are vectors. Now, if R is greater than n, then we say that automatically that the set S is linearly dependent. If R is less than n, so if R is greater than n, that's the first one, then the set S, I don't know why I keep on forgetting S, the set S is linearly dependent. If R is less than n, then the set S cannot span the vector space. Now, I talked about this before, but we use it now. If S contains at least two vectors that are scalar multiples of each other, then the set S is linearly dependent. Now let's look at this first problem, and some of the problems, if I can use the theorem here, definitely I will. So here, explain why S is not a basis for R2. Here's the reason why. Because they give us this the origin, then I mean it is a point, but it's like it's not a point in that sense in terms of structure wise. So for R2, we're looking for two vectors. We need two independent vectors. Some V1 and V2. Now this first vector is good, but this 0, 0, that doesn't help. The basis is set to be vectors that I can take any vector out there in that space and write it as a linear combination. I can't do that with this guy. So the set S, it fails on both accounts. It's not linearly independent because of 0, 0, because basically the set S is only acting with one vector, because this other vector, he's sickly. I mean, he's really like just not functioning, basically. So S is not linearly independent. S does not span, because anytime you have that origin vector like that, you can rest assured that's the conclusion. So here S is not a basis because both of the criteria fail. Now look at this one. Explain why S is not a basis for R2. Look at these two vectors. Notice that the two vectors are scalar multiples of each other. If I can take the number 2 times the first vector gives me the second vector. So if vectors are scalar multiples of each other, then that means that they are linearly dependent. And if they're scalar multiples of each other, they cannot span the vector space. What this really means is that only have one vector, 6, 5. So this is just like the previous problem. So with one vector there within R2, for R2 I need two vectors. I need two fully functioning vectors that are not sick. And I guess I keep talking about sickness because we're dealing with the coronavirus, right? So there's only one vector operating there. Now go back. If if S contains at least two vectors that are scalar multiples of each other, then the set is linearly dependent. So they're linearly dependent, but they also cannot span. Um, Now, how come they can't span? Check this out. There are two vectors, but there's actually only one, right? Because they're scalar multiples of each other. So there's only one vector. So you go back to the theorem, it says that, number two, if R is less than N, that's what we have. I only have one vector within the two space. Then that means that the set does not span Rn. So that's why we have this third conclusion there. So the next one, explain why S is not a basis for R2. Now watch this. Here for R2, N is equal to 2. But for S, R is equal to 3. So we said that when R is greater than N, that means then that we have the set S is linearly dependent. You see that? R is greater than N. There are three vectors, but the space only allows two. So I'm overcrowding the space. Let's go back to the theorem. We have this one here. R is greater than N. So the set is linearly dependent. See that? So it's good to have that pretty cool theorem, right? Now, explain why S is not a basis for R3. Here, R3, N is equal to 3, but here I have three vectors. R is equal to 3. So that theorem that I was using right here, I can't apply, right? Because I don't have R greater than N or R less than N, right? So very good. Now here's what I do. I take these vectors and I stand them up because they want to be a man. I stand them up and I just check the determinant. And because of the monster theorem, if you check the determinant, if the determinant is equal to 0, that means all bets are off. That means everything fails. You know, I need to put the right monster theorem. I copied in that last lecture, I gave you what this current textbook gave you. I didn't give you the old stuff. The old stuff is a whole lot better. If I'm thinking, man, for the next time I come in here and talk, I'm going to put the monster theorem. I need to put a little video. I did that one semester in class. I brought up Godzilla. Well, it was pretty good. You know, you bring up a dude like that. But anyway, the old one has everything in there. It has linearly independence and spanning. It has all that. That's what you need. But you check that determinant. If that determinant is equal to 0, that means all bets are off. That means that the matrix is not invertible. It means that the system AX equal to 0 does not give you the trivial solution. That's linearly independence. It means that AX equal to B does not have the unique solution. That's the spanning, right? So everything here fails because I checked one thing, and that was the determinant. Okay. So if the numbers match, if I have three vectors and the third space, check the determinant, right? If the determinant is not equal to 0, that's what you want, then that means that the set it does everything. It's linearly independent and it spans. All right, let's look at this one. Here, N is equal to 3. This is the third space. But watch this. R is equal to 4. And that guy messes us up. So for this one, here, R is greater than N. 4 is bigger than 3. So again, based on our theorem,
That's not the one.
is number 1, right? R is greater than N, so the set is linearly dependent. Okay? So that's it. Let's look at this one. Explain why here S is not a basis for for P2. Let's look at that. So I'm going to write out S. Here S consists of 1, 2, 3, 4 vectors. I'm going to call them V1, V2, V3, and V4. Now what are they? So V1 is equal to 1, but I'm going to write it out that this is really 1 comma 0 comma 0. If I'm in the polynomial space of 2, that means that its size is 2 plus 1. Remember, it's n plus 1 because of the coefficient. V sub 2.
Oh, things would be a whole lot better if I could count.
So V sub 2, it has that 9x, but there's no constant term. So it's 0, and then 9, and then there's no x squared term, so that's 0. V sub 3 is negative 2 comma 0 comma 1. And V sub 4 is 0, 5 comma 0. Now check this out. R is equal to 4. But here, I got n plus 1, is equal to 3, but it's really just n equal to 3. That is that the space of polynomials of the 2 space only allows for 3 vectors. And so here again you have R is greater than N. That's why you get linearly dependent. Okay? Okay, for this one, again, we're in this P2, so that means that the size is 3. How many vectors do we have? 1, 2, we got 3 of them. So look at the V sub 1 is 1 comma negative 1 comma 0. V sub 2 is 1 comma 0 comma negative 1. I'm looking there, right? And then V sub 3 is negative 1, negative 8, and 9. Well, there's 3 of them. Good. R is equal to 3. So for that one, I check the determinant. So this first vector, he stands up. Second vector, he stands up. Third vector stands up. Put that in my graphing calculator, check the determinant. I get 0. So that means that if you get 0, that means that both fails. The set is dependent, and the set does not span P2. That determinant is something else, right? All right, let's look at this one. All right, so here, determine whether S is a basis for the indicated vector space. So I got 3 vectors in S, so R is equal to 3, and we're talking about the third space, so I check the determinant. Check the determinant here. you get 0. So that means that S it does not span. Is this set is not linearly independent. This set is linearly dependent. This set is not a basis. Now, what makes it not a basis? Just one of them could fail, right? Um, and so now it's possible that you can have a set where they may span, but it may not be linearly independent. Doesn't matter. It's still not a basis. Or the vectors may span, but they may not be linearly independent. Hopefully I said that right. But if one is right, the other one's wrong, and if the first one's right, well, the first one's wrong, the other one's right. Blah blah blah. Okay, I don't want to get myself confused. I had lunch earlier today, and I didn't have that much. Um, okay, I lied. I ate a whole lot. Um, so anyway, determinant is equal to 0 from the Monsters theorem. That tells us that the trivial solution it does not exist, so it's not linearly independent, and ax equal to b does not have the unique solution, so it does not span. So good. Now determine whether S is a basis for R3. So it's R3 and I have three vectors. Good. So I check the determinant. Here the determinant is not equal to 0. So that means then that here S is a basis. So if S is a basis, then what can you do with that? Well, several things. Here is one of the coolest things, and here's exactly what it means. If a set forms a basis, you can take those vectors and you can write them as a linear combination of any vector out there that you want to form. Now, in the long run, what that's going to do for us is that there are vectors out there that we can't see, but we know they're out there. So this theorem is not just a uniqueness theorem. It's also an existence theorem. It says that something exists. That if the set spans, if the set forms a linearly independent set of vectors, then any vector out there can be written as a linear combination of these vectors. I can produce all those vectors out there exist because of the potency and the magnitude of this theorem. So we use that here. Since we know that these three vectors are linearly independent and that they span, that they form a basis. So if S is a basis for R3, which it is, then here's this. That's that arbitrary vector in that definition for the spanning. It's not arbitrary anymore. They've actually claimed it. So remember I was calling that B vector, right? So here what was dreamt about has come to life. Can we write U as a linear combination of the vectors in S? Well, yes, we can. So you remember how we do that is that basically we say that there exists scalars K1, K2, K3 such that K1 times, let's give these vectors some names. Okay, I'll call them V1, U1, U2, U3. Times U1 plus K2 times U sub 2 plus K sub 3 times U sub 3 is equal to this vector U. So now that implies that we have, let's make that smaller. I have this scalar times U sub 1, that's 4, 3, 5, plus K sub 2 times U sub 2, 0, 3, 5, plus K sub 3 times U sub 3. All they're doing is just taking the definition for linear combination, which is right out of the spanning book, right? U sub 3, 0, 0, 5. That's equal to the vector u, which is 8, 3, 20. Now, you write that as a matrix, and this is what that is. And so then you reduce that on your calculator, and you get the values that you want. Matter of fact, here u is equal to, this is 2 times, that is, look, k sub 1 is equal to 2. K sub 2 is equal to negative 1. K sub 3 is equal to 3. So I can write this vector u as 2 times u sub 1 minus 1 times, that's the minus 1, minus 1 times u sub 2 plus 3 times u sub 3. Isn't that a daisy? Yeah. So for dimension, pretty cool stuff. The dimension of and we've been talking about it already, the dimension of a finite dimensional vector space V is denoted by here, this dimension, and is defined as the number of vectors in the basis for V. So for R3, the dimension of V is equal to 3. For Rn, its dimension, I guess I need to write exactly what we're talking about, is equal to n. The dimension of the polynomial space of nth degree is n plus 1. The dimension of the space of n by n matrices is n times n. Okay. All bases in a finite dimensional vector space have the same number of vectors. That, what they're saying is that if you're looking at here Rn, then the basis for any if this is Rn and say this is a basis, this is a basis, this is a basis, it's only going to be 3 vectors in here, right? N equal to 3, n equal to 3, n equal to 3. Oops. That guy. Okay, last problem. And these problems should definitely get you through this section. Pretty cool stuff. Find a basis for the dimension of the subspace W of R4. So we're in the space of R4. So here it says that this subspace, we have the values 4s minus t, s, 3t, and s. Basically, it was an infinitely many solution set. S and t are the parameters. So so we're going to write that out. And so this basis looks like exactly what I'm given. So what am I given? I'm given for that first term, I'm given 4s minus t. That next term I'm given s. The third term I'm given 3t. And then the fourth term I'm given s. So we write that out. I only have 2 terms operating, s and t. So what that looks like is 4s, let's write everything with the s in them. S, that's a 0 there. And then s plus, now let's write everything with the t, negative t, 0, 3t, and 0. Now we write that out, This is 4, 1, 0, and 1 times s plus negative 1, 0, 3, and 0 times t. Okay, so what those numbers would be then would be 4, 1, 0, and 1 for the first vector. That's the base. That's the first vector for the basis for this so-called solution space, actually. And then this is negative 1, 0, 3, and 0. Now I have two vectors here. So these two vectors forms the basis, and this dimension of W. How many vectors do I have? Count the number of vectors I have in the basis. I have 2. And that's it. Okay. So hopefully that'll get you going, and you all be good.